Good. So let's start the meeting. So previous time we talked about cubic time and all pair shortest path problem. And we mentioned several other problems that they are equivalent or they are open, that whether they are equivalent with all pair shortest paths. In particular, whether diameter is equivalent of all pair shortest path or not, which is a big open problem now. Today we are going, instead of order n to the 3, we are going order n to the 2. And we are considering quadratic problems, which are hard. So in particular, the problem that we would like to consider is the three-sum problem. So what is the three-sum problem? So here you are given a set of n integers, and these integers can be, even have some kind of repetition. So one number may appear more than one time. And even we can additionally assume that the set is between minus n to the 3 to n to the 3. Note that this is important. Again, when we are further assuming that for the hardness, if you want to solve a problem, you want to get it as general as possible. But for the hardness, you want to solve the problem when or say the problem is hard, even for very specific case, because you may use those specific things for other problems. So here we say that even you're assuming these numbers are integers and everything is polynomial, even it's like at most minus n to the 3 to the n to the 3. Now, what is the problem? The problem is that whether there are three numbers a plus b plus c, all of them belong to B and C, they belong to S, such that their sum is equal to 0. By the way, you are seeing the shared screen, correct?
Yes.
Great. Okay. So this is whether there are three numbers that their sum is equal to 0 or not. So is the problem clear? Three-sum problem? Okay. So for this problem, there is a simple O tilde n to the t. O tilde means essentially general order n poly like n to the 2 poly n. So tilde means always some poly which are somehow hidden here. So in this case, so there is a simple algorithm n to the 2 poly n. How can we obtain this? So it is very easy. Take any two numbers, A and B, belong to S, and then sort S So this is order n square already. Then we are sorting S, which is order n log n. And finally, what do we do? So then we are searching, we are doing binary search. Which number? Minus A minus B. And for this one, we are paying a log n. So what is the result? The result that we have would be this, because for each pair AB, we are doing these log n operations. So the final things would be n to the 2 log n. So this is the algorithm. And that is the one that I mentioned. This is O tilde n square. Later, we are discussing a true logarithmic algorithm for that there is no this like n things. And it is exactly n square. Good. So that was the solution for that. Is the solution clear? Please unmute and answer. Any question about it? Good. So let's go for the, let me clean these things. No. So note the concept of subquadratic reduction from A to B. So what is that? We say that there is a subquadratic. Always when we say from A, it means that we want to solve A. So we want to solve A using B. So it means that if there is a truly subcubic algorithm for B, then we can obtain a truly subcubic algorithm for A. And truly subcubic here, here by subquadratic, I mean. Truly subquadratic means n to the 2 minus epsilon for epsilon greater than 0, some constant epsilon. Good. So what is the main conjecture? The main conjecture is that this is the three-sum conjecture, like all pair shortest path, that this three-sum is truly subcubic, is truly quadratic. So what is that? It means that the three-sum does not have truly quadratic time algorithm. It means that there is no algorithm of n to the 2 minus epsilon for some constant epsilon greater than 0 for the three-sum problem. And lots of people believe in that. So what is the general idea? The general idea is that essentially for any set S that you have, for any set S that you have it here, you want to say the best way to solve a three-sum is that you consider at least any two of them, and how many choices we have essentially, because we can have the repetition, is n square choices, and that's the only way that you can solve this three-sum problem. But the way, that is an interesting problem. This is one of the problems that if you go for some of the interviews or something like this, it is the problem also in the lead code. So what is the n square algorithm for that? There are versions of that. You can define also, like we are talking about the three-sum, you can think about the four-sum. How do you solve the four-sum problem? Or five-sum or others. So that's also interesting to like, can we do better for the, like say for four sums, is for four sum is a, you need to also get n to the 3. Of course, n to the 3 exists for four sum, but can you do n square? You can think about this one as an exercise. So this is for four sum problem. You want to see whether you can do n square or you need n cube. That's an interesting assignment. Good. Now, great. So let's. There are lots of 1 second. Better. Do you hear me now? Please unmute and answer.
Yes.
Great. Okay. So let's go to this one. And this. So there are lots of hardness based on the threesome conjecture for different problems. For example, if you see this paper of Abbott and Williams in 2014 in Fox paper, they are using this to solve for dynamic problems. So what is a dynamic problem? A dynamic problem, these are again a set of algorithms that we don't have a chance to go through them, but these are also important set of problems. Like this class in some sense is a advanced algorithms class that we talk about very different areas of algorithms, and we talk some upper bounds or some algorithm, and we focus mainly on the lower bounds after that. But dynamic algorithms are very important. So in the dynamic algorithms, you know that the input comes one by one. So you don't have the whole graph, for example, or the whole set at the beginning. So then we have two operations generally. We have the insertion, that you are inserting the data or inserting the items, like for example, the edges of the graph that you are inserting, or even the vertices of the graph that you are inserting. And then deletions. So you may delete vertices or edges at any time, or the items. So this is the main difference between regular algorithm and dynamic algorithm. So in the dynamic algorithm, we have both insertion and deletion. And the main things that we want to do it is the update time. So we try to bound update time. Often we try to get some kind of average or worst case. So worst case update time. So these two we are doing for update time. That's the main difference. We have the insertions and deletions, and we want to make sure that at any time the final graph is the graph that we have after all insertion and deletion, and we want to make sure that the average or worst case update time is bounded. So now for this set of problems, this is this paper of Abbott and Williams. That's actually good one to see what are the dynamic algorithm and how can we get the hardness results. So here they show actually several of these problems are if you want to get the dynamic problems, then the update time, for example, is at least some time because of using this threesome conjecture. Please, you may take a look at this paper. And I think we discussed before that, we really talk about so far about two important things. We talk about the truly cubic or truly subcubic and truly subquadratic algorithm. But maybe we don't talk about truly sublinear. We talk about them when we talk about local algorithms and others, but then we don't have an exact or we don't aim for the exact algorithm in this case, because the general idea is that at least you need to read the input, and reading the input at least takes omega n. And if there is actually part of the input you don't really need to read it, maybe you can just ignore those parts, and that might be they may not be part of the input at all. Good. Now, given that, let's go and talk about several threesome hard problems. These are, a nice set of problems that we discussed. First problem is the threesome problem. Okay. So what is the three-sum problem? Let me actually. We can make it a bit larger as well. Good. Okay. So what is the three-sum prime? So again, when we consider with lower bounds, we try to get more restrictions of the problem and say that they are actually hard. So in the three-sum, we had these things that you have one set S, and you wanted to find three numbers A, B, and C belonging to S that their sum is equal to 0. And of course, A and B or C can be repeated as well. Like you may use one element more than that. But that's a bit, I mean, maybe not the best one for the reductions. We have another problem, three-sum prime. What is that? Here we are given three explicit set A, B, and C. And the goal is that find A belongs to A, B belongs to B, and C belongs to C, such that A plus B is equal to C. Here it is, I mean, we could easily say that A plus, so we could easily say that A plus B is equal to minus C, because we can just inverse all elements of C. And then if A plus B is equal to minus C, means that A plus B plus C is equal to 0. So that we could do it. So it's not really a problem that we have this requirement, A plus B is equal to C. Now, one thing is that we want to say first reduction from three-sum to three-sum prime. Again, what's the meaning of that? It means that we want to solve three-sum using three-sum prime. How come? So it is very easy. So that you just do this one. You will put A equal to S, B equal to S, and C equal to minus S. So just put all three of them equal, like essentially two of them equal to S and the other one minus. And the minus exactly because of the difference that I have mentioned. Because in the three-sum, we want to have A plus B plus C equal to 0. And in the three-sum prime, we wanted A plus B is equal to C. So that's the only difference, and that's the reason that we have minus S. Other than that, we are just taking each of them is equal to S. So that's the, I mean, easy part. Now the more interesting part is this one, from three-sum prime to three-sum. Good. Let me just clean everything. Any question so far? Okay. So from three-sum prime to three-sum, this part is a bit more involved. Why? Because we have three sets A, B, and C, and we want to turn all of them into just one set S. The idea is that we have a different range for A, B, and C in S. So that's the whole idea. Such that we can, because here we need to force that A comes from A, B comes from B, and C comes from C. We don't have such a requirement in S. And that's exactly the reason that this three-sum prime is a easier problem to work with than three-sum itself. So how can we do that? We can have a different range essentially for A, B, and C in S when we want to put it. So the first assumption that all elements in A, B, and C are positive. So that is easy. Why not? Because if some of them are negative, we can just find the most negative number and then minus of that number. We call it K. We can add this K to all elements of A and B and then 2K to the element of C. So just find the largest negative number in A, B, and C, and then call the minus of that or the absolute value of that negative number K, and then add K to A and B and 2K to elements of C. What about for, so we know that everything is positive now. Now let's define this number. So what is M? M is the 2 times max of A, B, and C. Find the max of A and B and C, and then 2 times that. Now that we have everything is positive and we have defined M, we can now define, so we want to put elements of A, B, and C in S in a different range. How do we do that? For each element A, we put the element A prime, which is A plus M in S. Let me just change this one. That would be easier to write. Good. So for each element A that we want to put it, so let's put it like this way. Maybe I can just erase some of this. Just okay. So let's erase this one. Then so for each A, we will put it A plus M. So A prime would be A plus M. So that's the element that we will put it in S. What about B? For B, we are doing this. For each element B, we are putting B prime, which is equal to B. Let's see. There's some issues with this way of doing that. Okay, so yeah, let's see whether it is good. So good. So for each B prime, we will put it B prime equal to B, and then we will put that one in S. Finally, for C, we are putting each element C prime, which is equal to minus C minus M. And again, M was this number. So M was this 2 times max of A, B, and C. So these are the elements that we will put it in S. So how many elements do we have in S? Please unmute and answer. So how many elements do we have in S?
I have a question before. Yes. Yeah, what do we mean by the total size of N? I mean, it's union, the size of the union, or the size of A plus the size of B?
No. Here we are talking M is the max of A, B, C. There is no size.
No, but
the size of S means the number of. I mean, so how many elements do we have in S?
Yes, okay. So in the threesome prime, we have 3 sets of integers A, B, and C of total size N. So the size of the size n is the size of each of.
Yes, say the size of each of them. Yes.
Okay. Okay. Thanks.
So in that case, what would be the size of S? So the size of S would be 3 times n, correct? Because I mean each of them has size n, and then we are putting for each element A, B, and C for each element A in A, B, or C, we are putting one element in S. So the size of each of them is n. The size of S would be 3s.
Yes.
Good.
Can we then assume that A, B, and C are pairwise disjoint?
I mean, yes, but it is not needed for this reduction. So A, B, and C, they may share some elements, but with this way of, so note that how do we put them here? So we will make them that they will be disjoint. The elements that we will put it for A, B, and C would be disjoints. The corresponding elements would be disjointed S, even though the original elements may not be distinct.
Okay, thank you.
Yeah, and actually we don't have this requirement, because when we do this reduction from 3-sum to 3-sum prime, we actually put A, B, and C equal to S in this case. Again, if something not clear, please ask me. I think that would be great. If you don't know something, it's completely fine. But if you don't know and don't ask, that is not fine. Good. So this is the whole reduction. And let's see why it works. Okay, so the first thing is that if there are 3 elements, A, B, and C, belonging to S. No, if there are A, B, and C, these 3 elements, so what is the goal? We want to solve 3-sum prime using 3-sum. So if there are these A, B, and C belongs to essentially like A, B, and C, then of course, if some of them, if we have A plus B equal to C in the 3-sum prime, then of course, then A prime plus B prime plus C prime is equal to 0 here. Why? Because here we have just we have just added M here. We had subtracted M here, and then we put it minus C here. So if we sum it up, these 3 numbers, then it would be equal to 0. So that one part is easy, that if A, B, and C, or originally from A, B, and C, the sets A, B, and C, and if A plus B is equal to C, then the sum of them would be 0 in S prime, in S. Now the part that would be more interesting is the reverse of that. So what is the reverse? The reverse is that here we have 3 numbers, A prime, B prime, and C prime, that the sum is equal to 0. And they are belonging to S. We want to say that in this case, we have also the case that A plus B is equal to C. So we want to say for anything that A prime plus B prime plus C prime is equal to 0, we have this condition that A plus B is equal to C. Good. Now, let's consider this case that A prime plus B prime plus C prime, they are equal to 0. So first, what do we want to say? And again, these are just 3 numbers. We don't know whether this A prime is necessarily come from that it is a corresponding element of A, B prime is a corresponding element of B, and C prime is a corresponding element of C. Or this is actually the one that we want to prove it. Good. So this is a very important property. So we have, note that what is the property that we have? We know that A prime here that we have created always is between m and 1.5 m. Why 1.5 m? Please unmute and answer.
Because you took m to be 2 times the max.
Exactly, because it's 2 times the max. So that means that essentially A prime is this one. Similarly, B prime also, it would be between 0 and half m, because we are putting just exactly, so this is the m, this is the one that we are putting for A, this is the one that we've put it for B. And finally for C, what would be that? It would be minus C minus m, which means that it is between minus 1.5 m and it would be less than m. Also, this is important. So, for example, we are assuming that all these elements are positive. So that means that we have this thing that it is less than, this B prime would be greater than 0. Or similarly, because we have A plus m, we know that A is greater than m. And finally here, we know that because the elements of C were greater than 0, then we know that when we sum it up here, that would be definitely less than minus m. So these less than things is very important. Now, let's assume that, I mean, we don't know this is A prime, B prime, and C prime, but we know that these are x plus y plus z is equal to 0 for 3 numbers x, y, and z belonging to S. So let's have it here. So we know that x plus y plus z is equal to 0. Now, what is the first thing? The first thing is that I think, let me just. So the first thing is that at most one element of these 3 elements can originally come from A. So this is the first claim. So at most one of these 3 elements can come from A. Why? Because if there are 2 elements are coming from A, then we know that the sum of these 2 elements would be greater than, so if there are, this is all of them proof by contradiction. So we will say that at most one of these 3 elements can originally come from A. Because assuming if there are 2 elements are coming, so say x and y without loss of generality, then this guy is greater than m. This guy is greater than m. Now, it means that the sum of them would be greater than 2m. However, the only negative guy that we have, it is from C. But we know that it is at most, so the negative part here is 1.5m. So this C guy actually cannot compensate this positive sum. So this is not possible. So the first thing is that we know that at most one of these 3 elements can originally come from C. Similarly, we can say this is the second claim. Only one element can come from C. Why? Because if there are 2 elements come from C, again, the sum of these guys would be less than minus 2m. So if 2 elements of x, y, z, they are coming from C, then the sum of them would be less than minus 2m. And the only positive guy that we have actually is A. And we know that A is at most, the positive part is at most 1.5. Good. So, so far it is good. So it means that we can have at most one element from A and one element from C. So of course, if we have exactly one element from A and one element from C, then the third guy should come from B, and then we are fine. Then we have this A plus B equal to C things. The only thing is that what about this does not happen? One other thing. So now for C, we have one more condition. So this is the third one. If we say that we know that this is the third condition that we have it actually here. So far we mentioned that at most one element from A, at most one element from C. And one thing we can say that, we can say actually for the element from C should be exactly 1. Why? Because elements of A and B are both positive. To get negative, we need to definitely have something from C. So here it means that we should have exactly 1 element from C. Now, we have this other condition that at least 1 element should come, at most 1 element should come from A. The only, and if there is exactly 1 element from A, then we are done because there is 1 element from B and then we can find these 3 elements. The only bad part that remains is that there are 2 elements are coming from B. So what about if there are 2 elements coming from B? So why this case is not possible? Please unmute and answer.
Because if there's like 1 element from C and 2 elements from B, the sum will still be negative.
Exactly, because these elements of B are at most, I mean, if there are 2 of them are coming, so we have 2 times half M, which is equal to M. However, we know that the element of C prime is, they are less than, so the other guys is less than minus M prime. So if we sum it, these 2 guys, then it would be negative, it will be not 0. So it means that it cannot be the case that the other 2 elements are from B, and so we know that it means that at most 1 of them can be from B. That means that essentially exactly 1 element comes from A, 1 element from B, and 1 element from C. Good. That's the whole proof for this. And this is important. So in some sense, this is the case that from the threesome, now we got a problem that is much easier to work with, namely threesome prime. Because this positive, negative, etc., we can always, we have some control over them. And we know that the first element should come from the first set, the second one should come from the second, and the third one should come from the third. Good. So any questions so far? Let me clear everything. Good. So this would be a good exercise to So you can actually prove similarly that k-sum and k-sum primes are equivalent as well. So essentially, again, the k-sum is that you have k numbers from k numbers A, B, C to like the k numbers such that their sum is equal to 0 in S. And then you can say that the equivalent of k-sum prime is that each of them are coming from a different set, A, B, and C, and the k sets. So that is a good exercise to do that. Now that we have this k-sum prime, this is a very, or a threesome prime, actually, we want to prove some other problems that are hard. So what is the problem? So this is a problem called a geom-based. So geom-based because it's like you can get lots of other hardness from that. So this is a geometric version of threesome in some sense. What is the problem? You are given a set of endpoints with integer coordinates and 3 horizontal lines, y equal to 0, y equal to 1, and y equal to 2. The question is that whether there exists a non-horizontal line containing these three of these points. So what is the question again? So you have these three sets. They have in different lines. So this is a essentially y equal to 2, y equal to 1, and y equal to 0. And so the question is that whether there is a line that goes through three of them or not. And that should be a non-horizontal line. Always should pass through that. Whether there is such a thing that exists, goes there or not. So how can we guess this one? So there is a subcubic reduction free so there is a subcubic reduction from 3 sum prime to geom base. What's the meaning of that? It means that essentially we can solve the so it means that we should be able to solve 3 sum prime using geom base. How can we do that? So consider again 3 elements. A belongs to A. The color. So we have this A plus belongs to A, B belongs to B, C belongs to C. By the way, this is one point for presentation. It is important that when you use it, I mean, you don't want to use the red color too much because some people, they may not see red quite well. That's the thing that always, I mean, better to don't use the red too much in your presentations. So we have A, B, and C. For A, we are putting a point 0, like A point 0. For B, we are putting a point B and 2. And finally, for C, we are putting a C over 2 minus 1. So these are the points that we are putting. So in some sense, A would be here. B would be, sorry, A would be here. B would be here. And C would be the middle guy. And the value of C would be, you don't put it C, we are putting C over 2 because we want to somehow be the average. So this is the reduction that we are doing from, this is the 3 sum prime. And this is essentially geom base. So from these numbers, we are actually putting these other numbers. Now let's see why do we have this one. So this is the main property that we want to using. So we want to have, if we have a line passing the points x1, y1 and x2, y2, then we have, this is the equations that we have it. So y minus y1 over y2 minus y1 is equal to x minus x1 over x2 minus x1. So let's see what will happen if we are putting these numbers there essentially. So if 3 of them are collinear, so if there are 3 of them are collinear, actually it means that we can we should have these things. We should have y3 minus y1 over y2 minus y1, which is equal to x3 minus x1, and finally x2 minus x1. So this is for the case that here we have these 3 numbers, actually, right here, x1, y1, x2, y2, and finally x3 y3. So if we have these three numbers that they are collinear, it means that we should have this property. Now, let's see that how come we can have this one. So let's here consider the y1 becomes this point. And then y2 is this, and y3 is this one. So if we have this one, then what would be y3 minus, so what would be x3, what would be y3 minus y1? So of course, y3 minus y1 would be 1. So I just putting these equations in this equation. Let me put it here. So what do we have it here? So we have here in this case, sorry, here actually I meant x1 y1 is equal to this x2. So these are the points that I will get it. So what is y1? y1 would be 0. So here, y3 minus y1 would be 3 over 2. Sorry, it would be 1 minus, here would be 1 minus 0. What is y2 minus y1? So what is y2 minus y1? Please unmute and answer.
Two.
Yeah, because here y2 minus 0 would be 2 minus 0 here. Now, what is x3 minus x1?
C by 2 minus A.
Yeah, C over 2 minus A. What about x2 minus x3?
B minus A.
That would be B minus A. Good. So now what do we have? We are just simplifying this one. Yeah.
I guess it should be x2 minus x1 instead.
Sorry. Yes, you're right. X2 minus x1. Thanks. So which is B minus A. Yes. So in that case, what do we have? We have essentially B minus A should be equal to 2 times that, which would be C minus 2A. Correct? So it means that essentially B plus A is equal to C. And that's it. So we are just using this formula, that line passing through x1, y1, and x2 or y2, or this other formula that if we have 3 points that are going through one line, they are collinear, we should have these equations. And that's it. Now, the same thing also you can say, there is a subquadratic reduction from geom base to sum prime, to 3 sum prime. So it is essentially just the reverse of this operation. For each point A belong to the first guy, we create an element in A. So the first line, the y equal to 0, we are putting the same elements there. So the same thing, exactly the reverse of this reduction that we have mentioned here. So this is the reverse of this direction. Now, for each point B belongs B and 2, we create an element B belongs to this. And for each element C belongs to the middle line, we are putting an element 2 times C in C. Here we had it exactly these things as well. You see, we had from C, we went C over 2, the reverse of it would be 2C essentially. And that's it. Again, you are writing these equations, and you know that if they are collinear, so they are collinear if and only if B plus A is equal to C. Does it make sense? Great. So that's about this. Let me just clear everything. Any questions so far? Good. So let's go to the next one. Let's see another. Let's see another three-sum hard problem. What is the problem? So this is the problem. So this is the 3 point on the line. So here you are given a set of points in the plane. Is there a line that contains at least 3 of these points? So it is, this problem is very, somehow similar to geom-based problem. However, there in the geom-based, we had these 3 lines, y equal to 0, y equal to 1, and y equal to 2. And in that case, we wanted to find one horizontal, non-horizontal line that goes through them. Here we are saying differently. So you are given a set of points. So these are the set of points that are, just use a different color for that. So you are given this set of points. They can be, other places. So these are the set of points that are given to me. And the question is that whether there is a line that goes through, 3 of them. So there is no this condition of non-horizontal or something like that. So, good. This is let's give actually this one. So let's give a subquadratic reduction from 3-sum to 3 points on the line. By the way, we talked about in the previous problem, we needed to make sure that all these reductions are happening in a subquadratic time. But sorry. But that is easy for the previous problem because you just take these points, and for each element you are making a point. I don't know, from the element A you will go create a point 0.A. Everything can be done in linear actually. So the same here. So when we talk about the subquadratic, so we need to make sure any preparation in the reduction that we are doing to give the input of this problem to the other one also done in subquadratic time. Almost all of them actually happening in n log n at most. Lots of them even linear. Now, what is this thing? We are given a set of so here we are giving actually working with 3-sum directly. So we are given a set S of n integers, and for each x belong to S, we transform it to this point x to the 3. Good. So this is the reduction. So there we had this reduction was a bit different because we couldn't have non-horizontal. We couldn't have a horizontal line. Here we don't have this one. Now let's this one again. So you will take 3 numbers A. We have number A, B, and C. And we know that the sum of A plus B plus C is equal to 0. So when we have this one, A plus B is equal to 0, so this is belong S. Now we are from each of these points, we consider the points A to the 3, B to the 3, and finally C C to the 3. And we want to say that this will be collinear if and only if a plus b is equal to, so this is, these are collinear. If and only if a plus b plus c is equal to 0. Okay, so how can we do that? Again, we are using the previous formula. I will just mention how do you do that. So we were using the formula that we mentioned. So if we want to say they are collinear, still the same formula works. So y3 minus y1 is equal to over y2 minus y1 is equal to here sorry. So we have here x3 minus x1. And here we have x2 minus x1. Now, let's just, these are the 3 points that we have it. Let's just put the formula there. Yeah. So what is the formula that we have it here? So the formula that we have it here would be this one. We have y3, which is c to the 3 minus y1 says is essentially a to the 3 point. This one either over b to the 3 minus a to the 3. So this would be equal to, now what is x3? X3 would be just c minus a here. And here, this one would be b minus a. Good. Now, we need to do that. Do you remember the formula for c to the 3 minus a to the 3? You know, it is equal to what? So anyone remember that? So actually we can c minus a, that you can factor out. So that would be equal to c minus a times c to the 2 plus ac plus a to the 2. That is it over, here we have it b minus a again, times b to the 2 plus ab plus a to the 2. So this is equal to c minus a over b minus a. So when you do that, you need to, I mean, just be like working with this algebra or math easily. So here you just cancel out these guys, cancel out these guys. And then we have this formula that, is it clear so far? Please unmute and answer.
Yes.
So is it, yeah, go ahead.
I have a question.
Yes.
So is it possible to cancel them out? Can't it be like, can A equal to C, for instance, in the three-sum problem? Like, did we assume that the numbers are distinct?
Good. Yeah, so that is the good case. I mean, of course, we can assume that they are distinct because we can have these reductions. That these guys actually are coming from a different, this reduction that we had it from three-sum to three-sum prime, we can actually make sure that these guys, A, B, and C would be distinct. They will be not the same numbers. because we can just create this set S. So in the reduction, we had this reduction that A, B, and C will be. So if you remember, in the reduction from three-sum prime to three-sum, we create an instance of three-sum such that A, B, and C are distinct. So we know that this problem is hard, the three-sum is hard if we have this assumption that A, B, and C should be distinct as well. So we can just use that, and we are assuming that these three numbers are not equal. Does it make sense?
Yes.
Okay. So yes, but I mean, the formula, you should check it. I didn't check it. You may, even if they are equal, it may work. But if not, you can just assume that without loss of generality of the hardness that these three numbers are not equal. So A is not equal to B, not equal to C. Okay, so we cancel out these ones. So let's do this one to finalize it. So we have this. Theta 2 plus AC plus A to the 2. It is equal to B to the 2 plus AB. By the way, I mentioned this one because this seems like the formula here is different from the previous case that we will put it. That one seems more easier, but this seems, how do they obtain this formula actually comes from these ideas. Now, here, when we have this one, we can again cancel out these two guys. Now, and then we can write these guys as this one. So with this one, we can write C times A plus C is equal to so C times A plus C, here we have it, and the other one we have B times A plus B. I will just mention this one, you can actually get it more formally, but I just want to say that. So if you have A plus B plus C is equal to 0, then we know that A plus B is equal to minus C. So let's put the formula there. So if we put this one, so we have B times minus C here. And here we have it C times A plus C here. So then this C will be canceled out here. And we have this formula that A plus B plus C is equal to 0. So if you have A plus B equal to 0, this would be equivalent of this formula. It is not, I mean, you can just do an exercise. I mentioned that if we have that, then we have this equation, but this is essentially if and only if case. So you have these equations if and only if this condition is satisfied. I just mentioned one direction. You can do it as an exercise, the other direction as well. But this is somehow gives you the ideas that why we should have these things. So you can prove by contradiction. So that if A plus B plus C is not equal to epsilon, then what will happen? And then you get the equation. Anyhow, so that is a different formula, but it shows that actually this is when you go to the powers of 3, this kind of the going through line and having A plus B plus C is equal to 0, that would be the same problem. Does it make sense? Any questions? Oh, yes, we do just see it better. I think I can just Maybe put this one is a smaller font so you can just see the whole thing. Great. So let me clear everything. And then okay, so there is another problem, which is that's actually the dual of this points on tree line. So what is point in tree line? So the point on tree line. So given a set of lines in the plane, is there a point that lies on at least 3 of them? So essentially, you are given such a lines. So the question is that whether there are 3 lines that they are going through 3 of them. So this is an important problem. So this is this reduction, this duality. You can read it. There is also in the big Wikipedia. So there is this 3, like a point on 3 lines and 3 point on a line are dual. There are some famous transformations in the plane that they will take a point and make it a line, and they make a line to a point. So these are, I mean, some kind of geometric things that you can actually transform each line to a point and each point to a line. And under these reductions, I mean, these 2 problems would be essentially equivalent, because we already proved that for 3 points on a line, this problem is as hard as 3. Great. So, I mean, there are a few other problems that I will mention them next time. So these are a few other problems for which we also some geometric problems. So there are several of geometric problems that actually we show that, and we already showed that these problems are hard. I will talk a little bit more about this one. So and then we will go. So far, what was the thing that we discussed? So we talk about MP hardness, like the or MP completeness, PS space complete, and others. We mentioned several of these problems. We talk about 3 SAT and 3 partition. Then we came to the fine grain complexity. We talk about the 3 sum, or quadratic time and all pair shortest path, or cubic time. Then we will go actually to the big data. This is something that we will call it in the book under NP, because this problem in some sense these are easier than NP, but still when we talk about the exact running time would be fine grained part, or when we talk about the big data, that would be with some constraint that we will put it there, still they will be hard to solve. And when we are done, then we will go next to the approximation algorithm and fixed parameter algorithm. These are the problems above NP. And so we had it below NP, above NP, and I mean we will talk also some problem in between. For example, time permitting, we talk about also some game theory problems also, which is actually below NP, and we will discuss them. So just yeah, make sure that you are working on the project, especially that's important, and that's it. Any questions? Great. So if there is no more questions, I think we can finish the class today.